Noche Cósmica.
On a clear night, when the city lights fade and the sky opens above you, there exists a peculiar kind of silence, not the absence of sound, but something deeper, the stillness of distance itself. Thousands of points of light hang in that darkness, each one a sun or a distant flame, and most of them move through the heavens in ways so slow, so imperceptible to human timescale, that to our eyes they seem fixed forever. Yet among those ancient, patient stars, there are others, hidden from sight to the naked eye, spinning in the deep of space, are objects so strange and so precise in their behavior that when humanity first detected them, we were certain we had found a message from somewhere else entirely. These are pulsars, cosmic lighthouses, though we didn't know what we were looking at when we first heard their whisper in our instruments. A rhythmic pulse, a beat, a signal so regular, so mechanical in its repetition, that it seemed impossible it could be anything born from nature's chaos. And yet this discovery, when it finally came in the late 1960s, would reveal something far more wonderful than any alien greeting. It would show us that the universe keeps time in ways we had never imagined, that death itself could birth something eternal and precise, and that the sky above us holds secrets of such perfect regularity that we are still learning to listen to them. If you've ever felt the quiet unease of looking up at an infinite sky, the strange comfort of knowing that some things continue their ancient patterns whether we watch or not, then you might find yourself drawn to this corner of astronomy where destruction becomes elegance, where the collapse of stars gives birth to the most accurate clocks in existence. For more slow journeys through the quiet and hidden corners of the universe, moments like this one, where we pause to contemplate the deep, steady rhythms that hold all things in place, I invite you to subscribe to this channel, where we explore these restful truths together, one careful observation at a time. The night sky has always held a special place in human consciousness. For countless millennia, our ancestors looked upward into that darkness and saw patterns, constellations that wheeled predictably overhead, stars that returned to the same positions year after year, a cosmos that seemed ordered and knowable if only one could learn its language. There was comfort in that regularity. The Babylonians charted the movements of the planets. The Greeks built geometries to explain the heavens. And as the centuries passed, we came to understand that we lived within a system, that the stars obeyed laws, that beneath apparent chaos there existed profound mathematical order. What we could not have suspected, standing in our fields and cities, gazing up at that distant light, was that some of the stars we were seeing, or rather, some of the objects hidden among them, possessed a regularity so extreme, so perfect, that it would make the most precise instruments we could build seem almost crude by comparison. While we watched the slow procession of constellations across the seasons, somewhere in the darkness of the galaxy, invisible to our eyes, there were objects spinning hundreds of times every second, their rotation so steady that they could be used to measure time itself more accurately than the most exacting atomic clock. And we knew nothing about them. They were there all along, these cosmic heartbeats, sending out their regular pulses of radio waves, sweeping across space, like the beam of a lighthouse turning through the night. But lighthouses, at least, announce themselves. These were silent to us until very recently indeed. The moment of discovery, the instant when humanity first became aware that such things existed, belongs largely to one person's careful attention to detail. On August 6, 1967, in a small room at the Mullard Radio Observatory near Cambridge, a young graduate student named Jocelyn Bell Burnell was sitting before the output of a radio telescope, scanning through rolls of paper covered in the static scratches of cosmic noise. The telescope had been recording signals from distant quasars and other objects, and day after day, Belle Burnell would examine these paper records, looking for the telltale patterns that indicated a genuine astronomical object, as opposed to terrestrial interference. What she noticed on that particular strip of paper was unusual: a small, regular pulse. It appeared in the middle of the night, on a precise frequency, and it repeated with such consistency that it could not be random noise. The interval between each pulse was no more than a second and a third, and it continued pulse after pulse after pulse with an exactitude that seemed almost artificial. She marked the spot and continued scanning, but something in that pattern had lodged itself in her mind. Here was something that moved like clockwork, but moved across the night sky like a star. Something that sang with mechanical precision in a cosmos that we knew should be full of gradual, gentle changes. What could produce such a thing? The question, once asked, would not let go. For thousands upon thousands of years, humans gazed upward into the dark and found themselves held by something both intimate and infinite. The night sky was our first map, our first calendar, our first conversation with mystery. We traced patterns in the scattered light, drew lines between stars that had no actual connection except in our minds, and gave them names and stories: Orion the hunter, Cassiopeia the queen. We knew them by heart because they returned, night after night, in the same eternal dance. And in all those long centuries of watching, from Babylon to Egypt, from the highlands of Peru to the shores of ancient Greece, humanity developed a deep intuition about what the stars were supposed to do. They were eternal. They were constant. You could rely on them. A star would rise in the east and set in the west, the same star, performing the same arc across the sky, season after season, generation after generation. This predictability was comforting. It was almost like breathing. It was almost like a heartbeat. It was the rhythm upon which we built our sense of order in a world that often felt chaotic and uncertain. But here is something that no astronomer gazed upon for millennia, something no ancient observer ever consciously noticed. Some of those stars, a fraction so small we might never have spotted them without instruments, were not merely constant, they were flickering. Not with the gentle twinkle we see from Earth, that wavering caused by our own atmosphere, but with something far more precise. They were pulsing, they were flashing, with a regularity that would make a mechanical clock seem almost casual by comparison. And yet no one knew, no one could know. The human eye, as magnificent as it is, has limits. These pulses were happening too quickly, the light too faint, the telescopes of old far too crude to catch what was truly happening up there in the silence. What strikes us now, across that vast gulf of time, is how unaware we were of this extraordinary fact. A shepherd, watching the stars on a hillside in the ancient world, had no idea that woven into the patterns above were cosmic metronomes, stellar lighthouses spinning faster than a blade, each beam of radiation sweeping across the darkness with inhuman precision. The stars were keeping secrets. The universe had hidden within itself these objects of perfect, obsessive regularity, these points of light that would eventually tell us things about gravity and time and the very fabric of existence itself. There is a particular kind of wonder in this realization. For eons, the night sky was our canvas for contemplating the eternal and unchanging. We imagined the stars as fixed, as safe, as symbols of permanence in a brief and fragile life. And then, quite recently, in the span of human history, just a handful of decades ago, we discovered that some of those ancient lights were not eternal in the way we thought. They were not passive. They were not merely burning. They were doing something. They were working. They were keeping time. This is the paradox at the heart of the Pulsar story. These objects are among the most violent, most extreme things in the universe, born from the catastrophic death of massive stars, compressed into spaces so dense that a teaspoon of their material would weigh as much as a mountain on Earth. And yet their behavior, their output, their signal reaching across light years of empty space to our instruments, it is almost gentle in its orderliness. It is like finding a perfectly ticking clock inside a supernova. It is like discovering that chaos, taken to its absolute extreme, somehow resolves into rhythm. The ancient watchers of the sky could not have known this. They saw order in the stars because the stars appeared to offer it. They saw constancy because the patterns repeated. But they were only seeing what the naked eye could perceive, which is merely the surface of an incomparably deeper story. Somewhere in the catalogue of their names and myths, in the stories they told and retold, they were inadvertently cataloguing the locations of these hidden cosmic lighthouses: Betelgeuse, Vega, Sirius, Polaris. Some of these points of light, these ancient guides, had neutron stars nearby. Some were near pulsars that would not be discovered for another 2,000 years or more. This disconnect between what we see and what is actually there, between the peaceful night sky of human perception and the violent cosmic engines that make that peace possible, is what makes the Pulsar story so remarkable. It is a reminder that for all of human history, we have been surrounded by wonders we lacked the capacity to detect. We have walked under stars whose secrets would only yield themselves to the patient work of observation, to mathematics, to the slow accumulation of knowledge. And when those secrets finally began to reveal themselves, in the 20th century, in the work of a young woman sitting in a small observatory, listening carefully to the whispers of distant radio waves, the universe suddenly became a place even stranger and more beautiful than we had imagined. If you were an astronomer working at the Mullard Radio Observatory in Cambridge during the summer of 1967, you might have noticed something peculiar in the chart recordings that rolled out day after day from the radio telescope array. Those paper rolls collected whispers from the cosmos, faint signals translated into pen marks and patterns, and among all that static and stellar noise, one signal stood apart. It was so regular, so impossible in its steadiness, that the young astronomer who first spotted it almost dismissed it as interference. That astronomer was Jocelyn Bell Burnell, a 24-year-old graduate student working on her doctoral thesis, examining radio sources in the sky with the kind of meticulous attention that most of her peers reserved for important discoveries. She was, by all accounts, working through vast amounts of observational data, studying the twinkling patterns of distant radio galaxies, when she began to notice something that didn't quite belong. In the recordings from mid-August, there appeared a signal that pulsed with almost mechanical precision. It was faint, yes, but it was there. Regular, insistent, repeating every 1 1/3 seconds with a consistency that seemed to violate every law of natural astronomy she had learned. The signal came from a region of sky that would come to be called CP 1919, an ordinary-sounding designation for an extraordinary discovery. But Jocelyn, with the careful skepticism of a good scientist, didn't immediately declare that she had found something revolutionary. Instead, she did what any thorough researcher would do. She investigated. She looked at the signal from multiple angles. She examined whether it might be an artifact of the equipment, some electronic hiccup in the vast machinery of the radio telescope. She considered whether it might be a local source of interference, perhaps radar from a nearby airfield or some man-made radio transmission. The idea that this could be something genuinely cosmic seemed almost impossible. After all, the universe had never revealed such a thing before. By November of that year, after months of patient observation and careful analysis, the signal remained. It was still there, pulsing with that same eerie regularity, night after night. And by then, Jocelyn and her colleagues had begun to contemplate something far more extraordinary. Perhaps this was not a natural stellar object at all. Perhaps it was artificial. Perhaps it was a signal from elsewhere. The hypothesis was not spoken aloud without a certain embarrassment, but it was entertained. In those months of 1967, the possibility of detecting an intelligent signal from space felt just distant enough to be thrilling, yet close enough to warrant serious consideration. The researchers even gave the source a nickname, one born from scientific gallows humor, LGM-1, Little Green Men, the First. It was a way of acknowledging the unthinkable while maintaining the veneer of professional composure. If someone were to ask them what they were studying, they could speak of LGM-1 and let the questioner draw their own conclusions. But Jocelyn Bell Burnell, along with her supervisor Anthony Hewish and others in the research group, began to examine the signal with even greater precision. They looked at its timing. They measured the exact intervals between pulses. They observed how the signal's arrival time shifted slightly depending on the frequency at which they observed it, a phenomenon that would later reveal crucial information about the object's distance and nature. Every test, every measurement, every careful observation pointed toward a conclusion that was somehow both more mundane and more extraordinary than an alien transmission. This was not Little Green Men. This was something else entirely, something that nature had created through means unknown to science. The beauty of this discovery, if you consider how such things can be beautiful, was that it emerged from such careful, unglamorous work. There were no dramatic moments, no sudden flashes of insight in the middle of the night. There was only a young scientist, looking at paper recordings, noticing a pattern that shouldn't have been there, and then methodically, patiently, pursuing the truth of what she had found. The world of astronomy had been waiting, perhaps without knowing it, for someone to see this pattern, and Jocelyn Bell Burnell had been the one who saw it. By December, the discovery was ready to be announced. Anthony Hewish would present the findings to the astronomical community, and within weeks, the implications would begin to unfold. But in those quiet months between August and December, while the signal continued its steady pulse from across the light years, there had been this moment of genuine mystery. There had been the possibility, however briefly, that humanity had encountered something not yet understood, and there had been one young scientist, attentive and careful, whose willingness to notice something out of place had changed forever how we understand the universe's architecture. What is remarkable about this discovery, from the perspective of someone contemplating the cosmos at night, is how it reminds us that the universe can reveal its secrets only to those who are patient enough to listen, careful enough to observe, and brave enough to follow the evidence wherever it leads, even when that evidence points towards something that has never been seen before. The signal from CP1919 had been reaching Earth for perhaps thousands of years, crossing the vast emptiness of space, but only in 1967, only because of the combination of technological capability and human attention did its presence become known. When Jocelyn Bell Burnell first observed that peculiar radio signal, CP1919, the name it would carry in the scientific records, the initial reaction was not one of quiet wonder, but rather a kind of deliberate skepticism. The signal was too regular, too perfectly timed, arriving with the consistency of a metronome set to some cosmic tempo, and in that very regularity lay the first mystery to unravel. You see, the universe rarely offers such perfect precision. Stars twinkle and flare. Galaxies spin in their own chaotic rhythms. Yet here was something arriving with a regularity that seemed almost manufactured, almost artificial. The thought did occur to the research team, and they were not afraid to voice it. In those early weeks of 1967, when Bell Burnell and her colleagues gathered around their printouts and oscilloscopes, studying the endless parade of squiggles and pulses, someone voiced what would seem almost quaint in retrospect. Could this be a signal from an intelligent civilization? The idea was not as outlandish as it might sound now. The very steadiness of the pulse suggested intention, purpose, design, They even gave it an affectionate nickname, LGM-1, which stood for Little Green Men. There was a kind of humor in the naming, yes, but also a genuine line of inquiry that had to be followed to its logical conclusion. And so began the patient, methodical work of elimination. This is where science reveals itself not as revelation, but as careful listening, as a slow process of asking questions and ruling out possibilities, one by one, with the gentleness of someone sorting through a drawer in the darkness, feeling for the shape of what is true. The team considered every terrestrial source they could imagine. Could this be interference from radar installations nearby? They checked the timing against known radar sweeps. Could it be picking up television broadcasts, bouncing off something in the atmosphere? They examined the frequencies and the patterns. Could it be some piece of equipment in their own observatory, malfunctioning in some unusual way? They traced and retraced every wire, every transmitter, every possible source of man-made noise that might create such a signal. With each possibility examined and set aside, the truth began to emerge, not as a dramatic revelation, but as a quiet settling, like snow falling on a winter night. The signal was not being generated locally. The signal was not pulsing in response to anything the Earth was doing. What they were observing was coming from somewhere else entirely, somewhere out in the darkness above. But the presence of this signal, this profound steadiness arriving from the cosmos, did not necessarily mean intelligence. In fact, the very regularity that had first suggested artificiality would eventually point towards something far more elegant and far more natural. The universe, as it turned out, was capable of creating perfect clocks all on its own. You might wonder, as the researchers themselves surely did, how could nature manufacture such precision? What process could produce a signal so remarkably steady that it seemed almost impossible for it to arise from any natural phenomenon? The answer lay in understanding what had actually died to create it. For every pulsar visible to us now is, in essence, the corpse of a star, or more accurately, the densest, most compact remnant of a star that has ever existed. It is not living matter, not in the way we understand life. It is rather the ultimate expression of gravity's patient work, the final settling of matter into its most tightly bound state. This realization transformed the meaning of the signal. Once the team had ruled out interference, once they had eliminated every possible terrestrial explanation, what remained was not a message from elsewhere, but a message from deep time itself. The signal was a whisper traveling across light years, the faint echo of a catastrophic event that had occurred not recently, not in historical time, but in the deep past, perhaps millions of years ago. And what the team had discovered, quite by accident, was that the universe had been broadcasting this signal continuously, patiently, waiting for someone to develop the instruments and the curiosity to listen to it properly. The detective work did not end with simply identifying the source as extraterrestrial and natural rather than artificial. The investigators went further, asking new questions. If this was a natural phenomenon, then where was it located? How far away? What could possibly produce such a steady, mechanical rhythm? The answers to these questions would take shape gradually, through careful observation and patient analysis. But in those quiet weeks following the initial detection, when Belle Burnell and her colleagues were still in the process of ruling things out, something profound had already been discovered. It was not what they had initially suspected, not intelligence reaching out from the stars, but something perhaps more beautiful and more humbling. It was evidence that the cosmos itself could keep perfect time, that the universe contained its own clocks, scattered throughout the darkness, like lighthouses sending their beams across the vast distances between worlds. What remains after a massive star collapses, after all that light and fury fades, is something almost impossible to hold in the mind: a neutron star. Born from the innermost core of a star, perhaps 20 times the mass of our Sun, it represents one of nature's most extraordinary transformations, and perhaps one of the most calming to contemplate. Imagine, if you will, taking all the mass of that enormous stellar furnace, enough material to make hundreds of thousands of worlds like ours, and then compressing it, not gently, not over time, in an instant, collapsing inward upon itself with such tremendous force that the very atoms themselves begin to yield. The electrons are forced down into the protons, merging into neutrons, and what emerges is matter in a state so densely packed that a single teaspoon of neutron star material would weigh as much as an entire mountain on Earth. This seems impossible, and yet it is physics, written in the language of stars. The scale becomes dreamlike when you consider the proportions. This object, born from a star so large it would dwarf our Sun 1,000 times over, this collapsing inferno of stellar death, becomes something you could almost fit inside a city. The neutron star that is the heart of the Crab Nebula, born from a supernova explosion witnessed by ancient Chinese astronomers in the year 1054, measures only about 20 kilometers across. 20 kilometers, a distance you might drive across in 20 minutes on an ordinary highway. All that mass, all that stellar substance, compressed into something smaller than a metropolitan area. It is a thought that carries a strange quietness with it. The universe tends toward excess, toward vastness, toward the overwhelming. And yet here is an object that defies that expectation. Infinitely dense, yes. Extraordinarily powerful, certainly, but finite, graspable. A point in space you could almost imagine yourself standing at the edge of, looking inward at the most extreme concentration of matter nature permits under normal circumstances. The pressure at the center of a neutron star is so profound that it stops the collapse. The outward push of neutron degeneracy pressure, a quantum mechanical effect, a kind of cosmic resistance, holds the line against gravity's relentless squeeze, equilibrium, balance. Two opposing forces meeting in the dark, neither winning, both essential. The star does not continue to collapse toward a black hole, and the pressure does not dissipate. It simply holds, in a state of tension so precise, so delicate in its completeness, that the object remains stable for billions of years. What you must understand, as you drift toward the deeper parts of this story, is that the neutron star is not simply matter compressed, it is matter transformed. The neutrons themselves are crowded so tightly together that they begin to behave in ways that have no parallel in everyday experience. They touch each other, practically speaking. They cannot fall any closer without triggering those quantum forces that resist further compression. The result is a substance harder than anything your mind has perhaps encountered before, yet also perfectly ordinary from the perspective of the universe. This is just what happens. This is simply what remains. And within this extraordinary object, there is sometimes something equally remarkable. At the very heart, at the center where the pressure is most intense, physicists suspect there may be exotic forms of matter that defy even the standard model of particle physics. Quark matter, perhaps, matter composed of the most fundamental particles known, squeezed into configurations that exist nowhere else in the known universe. We do not yet know for certain. It is one of those gentle mysteries that hangs in the dark, awaiting future observation, future understanding. The interior structure of a neutron star remains partially opaque to us, and there is something restful about that uncertainty, something that invites quiet contemplation rather than anxiety. The surface, insofar as a neutron star has a surface, is itself strange and still not fully mapped by human understanding. It may be a thin crust of ordinary nuclear matter, nuclei compressed into a solid state, perhaps a kilometer deep. Beneath that crust lies the outer core, a region of neutrons in a quantum fluid state, moving and flowing in ways that have no counterpart at ordinary temperatures and densities. Further down, the inner core remains largely theoretical, a region where the very nature of matter becomes debatable. Yet for all this complexity, for all this density and this strangeness, the neutron star radiates remarkably little heat into space. It begins its life burning with residual thermal energy from the collapse, thousands of kilometers hot at its surface, but it cools slowly, over millions and billions of years, radiating away that energy into the vast emptiness around it. This gradual cooling, this slow and inexorable fading of its internal warmth, happens at a pace so measured, so patient, that it brings a sense of tranquility to the story of stellar death. Nothing happens quickly once the collapse is complete. Everything that follows unfolds in the grand, unhurried timescale of the cosmos. This is the foundation, then. This is what Jocelyn Bell Burnell's strange radio signals were bouncing off of. This is the source of those pulses, those cosmic heartbeats that would change our understanding of the universe and lead to a discovery so profound that it earned a Nobel Prize. But to understand how that heartbeat comes to be, you must first know what manner of object contains it. And now, as you settle deeper into this cosmic story, you know. A neutron star, born from collapse, infinitely dense, impossibly small, waiting in the darkness to share its secrets. Now, to understand what births this remarkable neutron star, this city-sized remnant of pure density, we must gently turn our attention to the process by which it comes into being. And here the language matters deeply. We speak of stellar death, and yet what occurs is less a violent ending than a profound transformation, a metamorphosis that unfolds across moments and leaves behind something fundamentally changed. Picture, if you will, a massive star in the twilight of its existence. This is not a star like our sun, which will fade quietly over billions of years. This is a star, perhaps 20 or 30 times more massive, a giant that has lived a short and luminous life measured in mere millions of years. For most of its existence, it has maintained a delicate equilibrium, the outward pressure of nuclear fusion in its core pushing against the inward pull of its own gravity, two forces locked in an eternal dance of balance. But fusion, as all transformations must, eventually reaches its limit. Deep within the star's core, the nuclear fuel runs dry. Hydrogen becomes helium. Helium becomes carbon and oxygen. Layer by layer, heavier elements form, each successive fusion process releasing less energy than the last. Each new element fusing in rings of increasing density around the core. And when iron forms, iron, which releases no energy when fused, the core reaches an impasse. The star has nowhere left to go. What happens next unfolds with a kind of terrible grace. The iron core, no longer supported by the outward pressure of fusion, collapses. Not gradually, but catastrophically, in less than a second. The electrons are forced into the protons. The core compresses to a density almost beyond comprehension. In that infinitesimal moment, the star's fate is sealed, and yet something extraordinary emerges from that collapse. The collapsing core rebounds. The infalling material crashes against the neutron star that has just formed at the heart of the star, and this collision generates a shock wave, a wave of unimaginable energy that races outward through the star's outer layers. And as that shock wave propagates outward, it ignites a final, furious burst of nuclear synthesis, a last echo of creation that sends the star's entire outer envelope into an outward rush of expansion and light. This is what we call a supernova, and here is where language and perception become essential. When we use the word explosion, we conjure images of violence, of destruction, of sudden catastrophe. Yet a supernova is better understood as a blooming, a star opening itself to the cosmos, The outer layers, which once held the pressure and heat of the star's interior, now expand at speeds of 30,000 kilometers per second. They cool as they expand, and as they cool, they begin to glow with an ethereal light. A supernova can, for a brief time, outshine an entire galaxy of billions of stars. And yet this brilliance is not aggressive, it is generous. It is the star releasing the elements it has forged over its lifetime. The carbon, the oxygen, the silicon, the iron, scattering them across the interstellar medium, gifting them to the universe. These are the atoms that will one day form new stars, new planets, new worlds. And at the very heart of this expanding shell of light sits the neutron star, born in the instant of collapse, waiting in darkness. For weeks and months after the initial explosion, the supernova's light gradually fades. The expanding shell of material grows larger and cooler. The shock wave weakens as it spreads into the surrounding space. Eventually, the nebula, the shell of expanding gas, becomes invisible to our eyes, though it will continue to expand for hundreds of thousands of years. All the while, at its center, the neutron star remains, already the most dense object short of a black hole, already set upon its path as a pulsar, already beginning to spin and send its lighthouse beam into the cosmos. What is remarkable about this process, when contemplated in the stillness of night, is how much of the star's life and identity is preserved. The neutron star does not emerge from chaos. It emerges from physics, from laws as precise and orderly as the ticking of a cosmic clock. And the electrons and protons that merge to form neutrons in that core, they were once part of the star's original composition. The neutron star is, in a sense, the star's essence distilled to its absolute minimum. Everything extraneous has been shed, only the fundamental remains. And perhaps this is why the process feels less like death and more like transformation, because the neutron star that emerges carries forward the star's momentum, its magnetic field, its relationship to the cosmos. The star has not been erased, it has been condensed, concentrated, intensified. It has become something more extreme, more pure, more precise than it ever was before. Can you sense, in that framing, a kind of mercy in the process, a gentleness beneath the apparent violence? The supernova is not the death of the star, but its metamorphosis. And from that metamorphosis, something emerges that will pulse steadily for billions of years, its rhythm steady as a heartbeat, its light reaching across the vast dark to touch our telescopes and our imaginations. A neutron star does not simply sit in the darkness, it turns. And as it turns, something extraordinary happens. The mathematics of rotation and magnetism conspire to create one of the universe's most orderly and deeply meditative phenomena. Imagine, if you will, a sphere the size of a city, yet containing the mass of our entire sun, spinning on its axis. The surface of this object moves with tremendous speed, and yet the motion itself is governed by laws so precise, so utterly reliable, that we can predict its behavior thousands of years into the future. This is the foundation of what makes a pulsar feel less like a violent cosmic object and more like a kind of universal metronome. At the heart of every pulsar is a magnetic field. This is not a weak field, not like the one that shields Earth or guides a compass needle across a table. The magnetic field of a neutron star is so powerful, so densely concentrated, that it warps the very fabric of space around the star's poles. Picture the field lines as threads extending outward from the star's north and south magnetic poles, spreading into the surrounding vacuum like the invisible strands of some cosmic web. These field lines do not remain still, they rotate with the star itself, spinning round and round, once every few seconds, or in the case of some pulsars, many times per second. The charged particles trapped within this field electrons and other subatomic fragments, are swept along by the rotating magnetic field, accelerated to nearly the speed of light. And here is where the lighthouse emerges from the machinery of physics. As these charged particles are swept along by the magnetic field, they emit radiation. This radiation is not emitted uniformly in all directions. Instead, it is beamed outward along the magnetic poles, concentrated into two narrow jets that stream away from the star like searchlight beams. The two beams point in opposite directions, emanating from the north and south poles respectively, and as the neutron star rotates, these beams sweep across the cosmos like the turning beam of a lighthouse on a dark, restless shore. If Earth happens to lie in the path of one of these beams, we detect a pulse of radio waves each time the beam sweeps past. If Earth does not lie in the beam's path, we detect nothing at all, and the pulsar remains invisible to us, spinning faithfully in the dark, its signal traveling harmlessly through the void. Consider the precision of this motion. The rotation of a neutron star is dictated by the principle of angular momentum conservation, a fundamental law of physics that feels almost like a kind of cosmic breathing. Just as your own breath follows a rhythm, in and out, steady and repetitive, the rotation of a pulsar follows a rhythm governed by the total angular momentum of the matter that created it. This angular momentum cannot be created or destroyed. It can only be redistributed. The faster a star rotates before its collapse, the faster its neutron star remnant will spin. In some cases, a neutron star may rotate just a few times per second. In others, it may rotate hundreds of times per second, a velocity so extreme that the surface of the star actually bulges outward, flattened at the poles by the centrifugal force. The magnetic beams, as they sweep through space, emit electromagnetic radiation across a broad spectrum: radio waves, light, X-rays, and gamma rays. The exact frequency and intensity depend on the strength of the magnetic field and the speed of the rotating charged particles. Yet regardless of these details, the fundamental pattern remains the same. There is a pulse, then there is silence, then there is a pulse again. The interval between pulses is determined solely by the rotation period of the star, and this interval remains extraordinarily stable. It is as though the universe has wound up a clock billions of years ago, set it spinning, and allowed it to tick onward with a regularity that human timekeeping can scarcely match. Think of your own breathing for a moment. In the quietest hours of sleep, your breath follows a rhythm: inhalation, exhalation, pause, inhalation again. The cycle repeats, steady and deep, thousands of times each night. A pulsar's rotation mirrors this pattern on a cosmic scale. The beam sweeps toward you. This is the inhalation, the arrival of a pulse. The beam passes, rotating onward. This is the exhale, the silence between pulses. The beam completes its arc through space, returns to point away from Earth, and continues its endless rotation. This is the pause, the waiting. And then, after a duration measured with absolute precision, the beam returns. The pulse arrives again. The rhythm reasserts itself, eternal and unchanging. The physics underlying this rhythm involves the interplay between rotation and magnetism in a regime that lies far beyond human experience. Yet there is something deeply soothing about contemplating it. In a universe that often seems chaotic, filled with explosions and collisions and the violent upheaval of stellar death, pulsars offer a counterpoint, a rhythm, a pattern, a kind of cosmic order that persists across the centuries. The magnetic field does not weaken and strengthen randomly. The rotation does not speed up and slow down without cause. Instead, both quantities evolve according to laws that can be written down, calculated, and understood. The universe, in this particular corner, is predictable. It is ordered. It is, in a way, at peace. Now imagine, for a moment, the peculiar sensation of witnessing perfect rhythm in a place where chaos otherwise reigns. A pulsar does not simply spin once, or twice, or even 10 times each second. Some of these neutron stars rotate with such velocity that they complete hundreds of rotations in the span of a single heartbeat, between 300 and 700 revolutions in just 1 second, 300 times per second. Let that settle into your mind without urgency, without strain. It is simply a fact, like the constancy of gravity or the slow migration of continents across geological time. The remarkable aspect, however, is not merely the speed of this rotation, but its precision. A pulsar's timing is so exquisitely accurate, so utterly unwavering, that it surpasses by orders of magnitude anything humanity has managed to construct. The atomic clocks that govern our telecommunications networks, the GPS satellites that guide ships across dark oceans, the synchronization protocols that hold the internet together, all of these depend upon devices whose accuracy is measured in trillionths of a second. Yet a pulsar spins with regularity that exceeds even these instruments. It does not drift, it does not falter, it simply turns, as it has turned for millions of years and will continue to turn for millions more. There is something almost calming about contemplating such steadiness. In our daily lives, we are surrounded by imprecision, clocks that lose seconds over weeks, heartbeats that quicken and slow with emotion and effort, the irregular cadence of breath as it responds to thought and circumstance. But a pulsar offers none of this variability. It is the embodiment of order. It is dependability given physical form. And from across thousands of light years, these signals reach us, unchanged in their fundamental character, as though the universe itself is breathing with a patience we rarely experience. The signal that arrives at a radio telescope on Earth from a distant pulsar carries within it this precision like an imprint. Consider what is actually happening in that moment. Your ears, or the speakers around you, are translating electromagnetic waves that began their journey when your ancestors had not yet learned to write. Waves that crossed the vacuum of space at light speed, undisturbed and undiminished in their regularity. When a pulsar with a period of, say, 0.2 of a second completes its rotation, a pulse of radiation sweeps past Earth, then nothing, then another pulse arrives, precisely 0.2 seconds later, and again, and again. The pattern repeats thousands or millions of times, never varying by more than a few billionths of a second. What might this feel like to perceive if one could somehow sense it directly? Perhaps it resembles the experience of listening to a metronome, but one so perfect it could mark the passing of epochs without drifting a single beat. There is a quality of rest in such uniformity. The mind does not struggle to anticipate the next pulse. It arrives exactly when expected. No surprises, no breaks in the rhythm, no sudden accelerations or mysterious pauses. Just the steady, eternal turning of a stellar corpse, its magnetic field sweeping through space like a lighthouse beam that has never once flickered or hesitated. The millisecond pulsars, those that spin even faster, completing their rotations in mere milliseconds rather than tenths of a second, carry this meditation even further into realms of constancy that seem almost abstract. A pulsar rotating 600 times per second maintains this precision so completely that if such a clock were placed on Earth at the moment dinosaurs walked among ferns and flowers, and were checked again today, in the time it would take for continents to shift and ice ages to rise and fall, the accumulated error would amount to only a few seconds, perhaps less, perhaps mere fractions of a second. And yet, in the midst of this perfection, there exists a gentle curiosity. Why does precision itself feel so restful to contemplate? Perhaps it is because the universe, on the scale at which we typically experience it, our weather, our seasons, the arc of our lives, presents itself as fundamentally unpredictable. We cannot say with certainty what the next moment will bring, but in the pulsar, we encounter something that says, with absolute conviction, what the next moment will be, and the moment after that, and the moment after that, for all of our brief, fleeting existence, and beyond into a future we will never see. The steadiness of a pulsar becomes, in contemplating it, a kind of anchor. It is a reminder that amid the flux and uncertainty that characterize terrestrial existence, there are structures in the universe that maintain an almost meditative consistency. They do not doubt, they do not falter, they do not require rest. They simply turn, with a regularity that would take a human lifetime to discern a single error. That reliability, that unwavering persistence, that absolute fidelity to a rhythm established by the laws of physics in the moment of its birth. There is something in the soul that finds profound comfort in recognizing such order reflected in the cosmos above. Now, within the universe's collection of these stellar metronomes, there exists a peculiar subset, pulsars that spin with almost unimaginable speed, far faster than their ordinary cousins. These are the millisecond pulsars, and their story is one of the gentlest dramas the cosmos has to offer, a waltz that unfolds across millions of years between two distant partners bound by gravity. For the longest time, astronomers were puzzled by their existence. How could a neutron star, born from the violent collapse of a massive stellar core, end up rotating hundreds of times in a single second? The initial pulsars discovered in the 1960s and 70s spun much more slowly, taking a full second or several seconds to complete one rotation. Millisecond pulsars seemed almost impossibly rapid, and the question hung in the air like starlight waiting to be understood. The answer, it turns out, lies in companionship, in the presence of a nearby stellar neighbor locked in an orbital embrace that lasts for eons. Imagine two stars orbiting one another in the darkness, separated by a distance that might be comparable to our Sun and Mercury, or perhaps closer still. One of them has already met its fate, collapsed into the dense, compact form of a neutron star. The other remains more ordinary, perhaps a red dwarf, a smaller star burning steadily through its hydrogen reserves. As the ordinary star ages, it swells. In the gentle language of astronomy, we say it evolves, expanding outward as it transitions through the phases of stellar life. And as it expands, its outer layers reach across the space between the two stars, drawn inevitably toward the neutron star's immense gravitational pull. This is not a violent siphoning, not really, but rather a slow, persistent draining of material. Gas flows from the expanding star toward the neutron star in a streamlined arc, a river of matter flowing through space itself. This gas does not fall straight down. Instead, it swirls inward in a spiral, forming what astronomers call an accretion disk, a rotating flat structure of gas and dust spiraling ever tighter around the neutron star's surface. Here is where the remarkable transformation begins. As the gas spirals inward, it is compressed and heated. The orbital motion of this infalling material creates an angular momentum, a rotational force that is transferred to the neutron star itself. Piece by piece, moment by moment, over millions of years, the accretion of this material spins the neutron star faster and faster. It is as though the companion star is gently spinning its partner up, like two dancers gradually increasing their tempo in a waltz so slow that human lifespans cannot perceive its acceleration. This process can continue for an extraordinarily long time. Some of these binary systems remain active, with material still flowing from the companion to the neutron star for many millions of years. During this epoch, the neutron star is gradually wound tighter and tighter, its rotation accelerating toward the remarkable speeds we observe today. A pulsar might spin up from a leisurely rotation of once per second to several hundred revolutions per second, and all of this happens not in a dramatic flourish, but in a patient, cosmic rhythm that stretches across geological and astronomical timescales. What is particularly soothing to contemplate is that these systems eventually evolve into a kind of stability. The neutron star may reach a point where the material being accreted is no longer significant, or the companion star may lose the outer layers that were being drawn away. At that moment, the spin-up epoch ends. The millisecond pulsar continues rotating at its achieved speed, no longer accelerating, but coasting through the universe as an extraordinarily precise clock, a testament to the gentle accumulation of angular momentum over millions of years. Some millisecond pulsars have been observed in systems where the companion is so close and the orbital period so short that we might call them intimate partners. The two objects complete their orbit in just a few hours, sometimes far less. Others orbit in wider, slower patterns, taking days or even months to complete a single revolution around their mutual center of gravity. Each system tells a unique story of how its particular millisecond pulsar came to be. There is something particularly moving about these systems when you consider their fate. Many of them will eventually settle into a quiet stability, the companion star continuing its own slow burn, while the neutron star spins on at its rapid pace, emitting its beam of radiation into the cosmos. Others may eventually merge. As the companion star loses more mass, it shrinks, and the orbital energy is gradually dissipated through the emission of gravitational waves, those ripples in space-time that Einstein predicted more than a century ago. Over eons, the two objects spiral slowly inward, drawing closer and closer, in a cosmic dance that accelerates only as the end approaches. But this process unfolds so gradually that it takes many millions of years. The couple orbits together in darkness, the millisecond pulsar flashing its beam into space with metronomic precision, while its companion circles nearby, and the universe itself carries away their orbital energy in the form of gravitational radiation, invisible and subtle. It is a reminder that even in the cosmos, some of the most profound transformations happen quietly, through the patient accumulation of small effects over vast expanses of time, through the gentle influence of gravity, and the persistent gift of material flowing from one star to another. Out in the void beyond Earth's orbit, where our mechanical emissaries drift through the silence of deep space, there exists something profound. The pulsar has become, quite literally, a map home. Imagine yourself inside one of these spacecraft, Voyager 1 or 2 perhaps, carrying within its instruments a kind of cosmic atlas, written not in ink or light, but in the precise timing signals of dying stars. These rotating neutron stars, with their metronomic beams sweeping across the darkness, have transformed into navigation markers more reliable than any satellite system we could build here on Earth. When engineers and astronomers began to understand the true nature of pulsars in those early years after their discovery, a curious possibility emerged. These celestial objects spin with such extraordinary regularity, some maintaining their rhythm for millions of years with barely a microsecond of deviation, that they function as nature's own atomic clocks, scattered like lighthouses across the galaxy. A spacecraft traveling through the interstellar medium, equipped with the right instrumentation to detect and measure the precise timing of pulsar signals arriving from different directions, could determine its location by triangulation alone. This is celestial navigation elevated to its purest form, stripped of satellites or ground stations, dependent only on the universe's own steady beacons. The beauty of this system lies in its independence. A spacecraft using pulsar navigation requires no communication with Earth, no transmission of signals back home, no waiting for responses through the vast delays that distance imposes. Instead, the vessel simply listens. It receives the faint radio waves emanating from these stellar remnants, measures the precise arrival times of each pulse, and from that information derives its position in space with remarkable accuracy. Over the course of a journey measured in years, as multiple pulsar signals accumulate and intersect, the spacecraft's location becomes increasingly clear, a three-dimensional position written in the language of cosmic geometry. But there is something even more profound encoded within the Voyager spacecraft, both 1 and 2, as they have journeyed beyond the boundaries of our solar system into the genuine depths of interstellar space. On each vessel rides a golden record, a time capsule of Earth and humanity created with extraordinary care in the mid-1970s, before either spacecraft began its ultimate voyage outward. On this record, alongside music and greetings and images from Earth, there exists a star map. Not a conventional star map as you might find in a terrestrial observatory, but rather a diagram intended to communicate to any possible extraterrestrial intelligence that might someday encounter the Voyager spacecraft, showing them where Earth is located within the galaxy. This map was created using pulsars. Specifically, it charts the positions and characteristics of 14 nearby pulsars, each represented by a line radiating outward from the position of our Sun. The idea, conceived by the scientists and engineers who assembled the Golden Record, was elegant and quietly moving. Any civilization advanced enough to detect the Voyager spacecraft and sophisticated enough to understand its origins would likely also understand pulsars. They would recognize these cosmic beacons in the diagram and be able to use the pulsar locations as reference points, triangulating backward to find the source, our modest spiral arm of the galaxy, our small yellow star, and the pale blue dot of Earth orbiting in the darkness. It is a way of saying, in the language of the cosmos itself, we are here, we exist, this is where you can find us. The pulsars chosen for this map were selected with care. They had to be relatively near Earth, within a distance from which they would remain identifiable markers from the perspective of a distant civilization. They had to be distinct enough, varying in their rotation periods and decay characteristics, so that together they formed a unique pattern, unmistakable and reliable. The lines radiating from our Sun's position were drawn with lengths proportional to the radio wave frequencies emitted by each pulsar, creating a kind of unique fingerprint written in pure mathematics. Should an intelligent species decode this record and understand pulsars, the logic becomes almost transparent. Follow these directions, and you will find the home of those who sent this message across the stars. There is something quiet and beautiful in this choice, when you consider it in those moments just before sleep, when the mind becomes receptive to such cosmic contemplations. Humanity, in its profound uncertainty about whether anyone else listens in the darkness, nevertheless chose to use not planets or bright stars, but pulsars, these remnants of catastrophic stellar death, these lighthouses born from the violent collapse of massive stars, as the fundamental language of our location. We said to any possible listener, know these cosmic clocks, and you know where we are. It speaks to a kind of humility and hope intertwined, the recognition that the universe's most reliable markers are not the largest things or the nearest things, but rather these dense, spinning beacons that rotate with a precision that rivals our greatest instruments. And so, as these spacecraft continue their eternal journeys, crossing the vast emptiness between stars, they carry forward this dual purpose. The sensitive instruments within them listen to the pulsar signals continuously, extracting ever more precise location data from the universe's cosmic grid. The golden record aboard them carries the same information, not to be read by machines but by minds, a message written in the steady rhythm of rotating neutron stars, an invitation framed in the language of pulsars themselves. It is navigation and communication merged into a single, serene concept. The universe's own heartbeat has become our compass and our way of reaching out across the darkness. Now, there exists in the heavens a pair of pulsars locked in an intimate cosmic waltz, orbiting one another in the silent dark, and their story carries within it one of the most profound confirmations of Einstein's vision of gravity itself. In the year 1974, two radio astronomers named Russell Hulse and Joseph Taylor were surveying the sky near the constellation Aquila when their instruments caught the unmistakable signature of a pulsar. It was a millisecond pulsar, spinning at a dizzying pace, and at first it seemed like any other stellar beacon, but as they continued their observations, night after night, they noticed something delicate yet undeniable in the data. The timing of the pulsar's signals, those radio pulses arriving with such metronomic precision, was subtly shifting. Sometimes the signals arrived a fraction of a second earlier than expected, sometimes later, in a gentle rhythm that repeated roughly every 7 hours and 45 minutes. This was not randomness. This was not noise in their equipment. This was a pattern, and patterns in astronomy are the language through which the cosmos reveals its secrets. What Hulse and Taylor had discovered was that the pulsar was not alone in its orbit through space. It had a companion, another massive star, likely another neutron star, itself perhaps a collapsed stellar remnant. Together, these two objects circled around their common center of gravity in an orbital dance, and the pulsar, by virtue of its extraordinary regularity, served as the most precise cosmic clock one could imagine. As the pulsar moved closer to and farther from Earth in its orbit, the Doppler shift of its signals painted the portrait of this hidden binary system. The real significance, however, lay not in the mere fact of this orbital partnership, but in what happened to that orbit over time. Einstein had predicted, decades earlier in his general theory of relativity, that two massive objects orbiting one another would gradually lose energy. They would not orbit with perfect constancy forever. Instead, according to his equations, they would spiral slowly inward, their orbital period gradually shortening, their dance accelerating in its final approach. This energy would be carried away by gravitational waves, ripples in space-time itself, traveling outward at the speed of light, distorting the very fabric of the universe as they passed. But in the 1970s, gravitational waves remained theoretical. No one had ever detected one directly. No one had ever measured the precise decay that Einstein predicted. Hulse and Taylor began their patient vigil. Night after night, month after month, year after year, they measured the exact moment when each pulse of radio energy arrived at Earth. They could determine with extraordinary precision whether the pulsar's orbit was changing, whether the orbital period was indeed shrinking in the manner that Einstein's equations proposed. It was a test that required patience, the very quality that makes for meditative science. There were no dramatic moments, no sudden revelations. There was only the steady accumulation of data, the slow gathering of evidence, like watching the hands of a clock move when you know intellectually that they are moving, yet you must observe long enough to witness the change yourself. And over the course of years, the data spoke with undeniable clarity. The Hulse-Taylor pulsar system was losing orbital energy at precisely the rate Einstein had predicted for gravitational wave radiation. The two neutron stars were spiraling toward one another, their orbital period shrinking by approximately 76 millionths of a second each year, an almost imperceptible amount, and yet measurable, confirmable, reproducible. It was as if the universe itself was nodding in agreement with Einstein's vision, confirming through this distant binary system what physicists had theorized but never observed. What makes this discovery particularly soothing to contemplate is its profound gentleness. This was not an explosion or a violent collision being measured. This was a slow, inevitable decay. The pulsar and its companion will not collide for several 100 million years. They spiral downward at a pace so gradual that if you were to observe the system continuously, you would perceive no change whatsoever. Only when years of observations are gathered and analyzed, only when the cumulative shifts are tallied with the precision that only atomic clocks can provide, does the truth emerge. It is a reminder that the greatest dramas of the cosmos often unfold on timescales that dwarf human perception, that the universe operates according to laws so precise and fundamental that they can be verified through the patient, methodical work of observation and measurement. The confirmation that Hulse and Taylor provided had profound implications. It was not merely that Einstein had been correct about this one prediction. Rather, it was that gravitational waves themselves must be real. They must exist, even though we could not yet detect them directly. The energy loss in the binary pulsar system could only be explained by the radiation of gravitational waves carrying away energy from the orbiting neutron stars. This quiet confirmation, derived from radio signals traveling across light years of space, from a pair of dead stars locked in an eternal embrace, became one of the most compelling pieces of evidence that the universe really does operate according to general relativity. It suggested that somewhere out there in the cosmos, other systems might be radiating gravitational waves so powerfully that someday, with sufficiently sensitive instruments, we might hear them. The Hulse-Taylor pulsar remains observable to this day. Astronomers continue to monitor its signals, continue to refine their measurements of orbital decay. Each new observation reinforces what Hulse and Taylor discovered, that Einstein's century-old equations continue to predict the behavior of the cosmos with extraordinary accuracy. And as you rest beneath the weight of your own thoughts, you might find comfort in the image of this binary system, two remnants of dead stars orbiting one another in the deep silence, confirming through their slow, inexorable spiral the fundamental laws that bind the universe together. They are engaged in a dance that will end in merger and collision, yet that endpoint lies so far in the future that it poses no urgency, no alarm. Instead, there is only the quiet certainty of orbital mechanics, the serene inevitability of gravity, the slow and patient validation of one human's intuition about the nature of space, time, and matter itself. What if you could listen to the universe breathing? Not with your ears, but with the steady rhythm of dozens of ancient stellar clocks scattered across the galaxy, their signals arriving at Earth like whispers from the dark. This is precisely what astronomers began attempting in the late 1980s and early 1990s, when they realized that pulsars offered something far more profound than individual cosmic timekeepers. Together, they could become a vast listening device, tuned to detect the gentlest vibrations moving through the fabric of space-time itself. The concept emerged slowly from a quiet observation. The signals from pulsars are so regular, so predictably precise, that even the smallest deviation from their expected arrival time becomes meaningful. Imagine having a network of the most accurate clocks ever created, distributed across thousands of light years, all ticking in synchrony. If something vast and powerful were to move through the universe between us and those distant clocks, it would create tiny waves in space-time itself, waves that would reach us before they reach the pulsars, or after, depending on the geometry. These disturbances would arrive as subtle shifts in timing, infinitesimal delays or advances in the pulse we receive from each stellar lighthouse. This is the profound elegance of pulsar timing arrays. By monitoring the arrival times of signals from dozens, eventually hundreds of pulsars simultaneously, astronomers could theoretically detect something that had long eluded direct observation: gravitational waves on the lowest frequencies, the deepest hum of the cosmos. Unlike the violent collisions of black holes or neutron stars that produce the high-frequency gravitational waves detected by laser interferometers like LIGO, these low-frequency waves move through space with a slower, gentler undulation. They are created by the orbital decay of supermassive black hole pairs at the centers of distant galaxies, binary systems so massive and so far away that their gravitational ripples take years or decades to pass through our solar system, leaving their trace written in the tiny temporal variations of pulsars. The work of establishing and maintaining pulsar timing arrays has been profoundly patient. Researchers around the world, particularly through arrays like the North American Nanohertz Observatory for Gravitational Waves, began collecting decades of observations, building a temporal record so precise it could detect shifts of mere microseconds. Imagine tracking the arrival of a heartbeat, not just over days or weeks, but across 20, 30, 40 years, accumulating enough data that the signal of a passing gravitational wave could finally rise above the noise of cosmic dust, interstellar weather, and instrumental uncertainty. The patience required mirrors the pulsars themselves, their steady spinning presence becoming an act of deep observation rather than passive reception. What makes this endeavor particularly soothing to consider is its fundamental quietness. There are no dramatic moments, no sudden flashes of light. Instead, there is the methodical, almost meditative work of astronomers around the world, logging data, analyzing timing residuals, comparing notes across networks. They are listening, genuinely listening, to the universe's lowest frequencies, the movements of objects so distant and so massive that their orbital motions take millions of years to complete. Yet despite this vast timescale, the signature of their gravity ripples through the cosmos at the speed of light, and pulsars capture it. In recent years, this endeavor has begun to yield fruit. In 2023, multiple pulsar timing array collaborations announced the tentative detection of a gravitational wave background, a stochastic hum underlying the universe itself. This was not the discovery of a single event, but rather the confirmation that the universe is constantly vibrating with the collective gravitational whispers of countless supermassive black hole binaries, their signals layered and interwoven across the cosmos. The announcement came quietly, not as a dramatic breakthrough, but as the natural conclusion of decades of careful observation, thousands of nights of telescope time devoted to monitoring the same pulsars, watching their pulses arrive, measuring the microseconds, building the case step by step. What is particularly poignant about this method is that it inverts our typical relationship with the universe. Rather than sending signals outward, hoping to detect reflected light or radiation from distant objects, astronomers here allow the universe to send its signals to us, encoded in the temporal behavior of the pulsars we already know and cherish. The pulsars become a kind of cosmic antenna, not transmitting information about themselves so much as allowing space-time itself to modulate their signals as gravitational waves pass through. It is a form of listening so subtle, so refined, that it almost feels like meditation rather than astronomy. The timing arrays also represent a form of gentle, distributed observation that honors the international nature of scientific work. Facilities in North America, Europe, Australia, and elsewhere contribute their measurements to common archives, pooling decades of observations into collaborative efforts. There is something deeply calming about this image, a global network of researchers, none of them likely to witness the definitive confirmation of gravitational waves in their own career, yet all of them contributing to a shared endeavor that will outlast them, a record that will only become more valuable as the data accumulates and the signal strengthens. The transition from studying individual pulsars to using them as components of a vast gravitational wave detector represents a shift in perspective that feels almost philosophical. Each pulsar, once understood as a stellar wonder in its own right, becomes part of something larger, a node in a vast sensor network distributed through space. Yet this does not diminish them. Rather, it elevates their significance. Their regularity, once appreciated for its own sake, becomes the foundation for one of humanity's deepest attempts to perceive the universe's most subtle motions, the slow dance of distant black holes whose gravity waves have been traveling through the darkness for millions of years. There exists in the cosmos a sibling to the pulsar, a being so extraordinarily magnetized that it seems to belong less to the realm of physics and more to the province of dreams. The magnetar is what astronomers call a neutron star that has been pushed to an even more extreme expression of itself, and yet there is something almost serene about how we might contemplate it, not as a threat, but as a marvel of nature's hidden architecture. Picture, if you will, the magnetic field you know from Earth, the gentle force that orients a compass needle toward the north. Magnetars possess magnetic fields not merely stronger, but incomprehensibly, almost unreasonably stronger. A typical pulsar's magnetism might be 1 trillion times that of Earth. A magnetar amplifies this tenfold, 100-fold, sometimes more. We speak of these fields in units called Gauss, a measurement that becomes difficult for the mind to hold, and yet the numbers themselves have a kind of hypnotic quality to them. A magnetar can harbor a field of 10 to the 15th Gauss or beyond, and at such scales, the magnetic force becomes something almost sculptural, almost architectural in its effect upon matter itself. If you were to bring a magnetar's magnetic field close enough to approach an ordinary atom, and this is a purely imaginative exercise, you understand, the field lines would begin to deform the electron clouds around the atom's nucleus. The very geometry of chemistry would bend and reshape. The bonds between atoms, the basis of all solid matter, would feel the pressure of this invisible force. The atoms would elongate, stretched along the field lines like taffy being pulled across an invisible loom. And yet there is nothing violent in this description if we simply observe it, witness it, understand it as a natural consequence of extreme density and extreme magnetism interacting with the rules of the universe as they truly are. The question that naturally arises is how magnetars come to exist at all. Do they form differently than pulsars, or are they perhaps the same object seen through a different lens? Here the waters grow a little murkier, and we might think of this as a gentle, open question, rather than a puzzle to be urgently solved. One prevailing theory suggests that magnetars may be born from progenitors different from ordinary pulsars, perhaps from stars with particularly strong magnetic fields before they collapsed. Or perhaps certain magnetars are simply younger pulsars, and they retain their extreme magnetism temporarily, slowly losing it over millions of years as all spinning objects gradually dissipate their energy. The distinction remains one that keeps astronomers thoughtfully engaged, observing and measuring and wondering. What makes a magnetar even more remarkable is how rarely we see one release its accumulated magnetic tension. A magnetar might sit silent for years, emitting only faint radio signals, much like its pulsar cousins. And then, without clear warning, or rather, with warnings that we are still learning to read, a magnetar undergoes what is called a starquake. The solid crust of the neutron star, harder than any material in the laboratory, suddenly shifts and cracks. The magnetic field lines, which had been wound tightly through and around the star, suddenly rearrange themselves. In an instant, the magnetar releases energy, a burst of X-rays and gamma rays that, despite being released across light years of distance, can briefly outshine all the other stars in that region of the galaxy, and then it falls quiet again. There is something oddly comforting in this narrative, even as we acknowledge the tremendous energies involved. The magnetar is not lashing out at random. It is following the laws of physics, obeying the same principles that govern a compass needle, a spinning ice skater, or the rotation of a distant galaxy. The violence, if we may call it that, is contained entirely within the object itself. From our perspective, from the vast distances across which we observe it, it is simply a star obeying its nature, releasing energy according to rules that are written into the fabric of reality itself. Some magnetars are also pulsars, and they rotate at their own particular rhythms, their magnetic beams sweeping across the darkness just as their cousins do. But there is a quality of unpredictability to the magnetar that sets it apart. A pulsar's radio signal is like a metronome in the night, steady and reliable. A magnetar's signal flickers, brightens, dims, sometimes disappears for a time before returning. It keeps astronomers alert, keeps them wondering what might be happening in the heart of such an object, deep within the crushing density where the rules of atoms and light themselves begin to bend and blur together. Think of it as the wild variation at the extreme end of a spectrum. Pulsars represent the cooler, more orderly end of neutron star existence, reliable as heartbeats. Magnetars are the passionate extreme, the place where the cosmos shows us what happens when you push all the knobs all the way up, when you combine the immensest density with the most enormous magnetic fields. And yet they, too, are subject to decay, to slow entropy, to the universe's patient drift toward disorder. Even magnetars will eventually cool, will lose their magnetic sharpness, will settle into quieter existence as ordinary neutron stars or dark stellar remnants. What remains most soothing to contemplate is that even these extreme objects are not aberrations or exceptions to the universe's rules. They are expressions of those rules taken to their logical conclusion, the universe's way of showing us what is possible when you compress a star's entire core into a sphere no wider than a city and set it spinning in a bath of forces beyond human intuition. They exist, they follow laws, they tell us something true about the nature of matter and energy and magnetism. And in that truth, there is a kind of elegance, a kind of peace that comes from knowing the universe operates by principles we can, slowly and carefully, come to understand. These cosmic lighthouses, so brilliant and precise in their youth, do not burn eternal. There exists in the physics of neutron stars a gradual surrender, a quiet dimming that unfolds across millions of years. As a pulsar spins, it radiates energy into the surrounding darkness. This energy does not come from nowhere. Each beam of radiation, each sweep of the magnetic field carrying particles outward into space, costs the star a small fraction of its rotational energy. Imagine a child spinning a top on a table. The friction of air, the wobble in its axis, the inevitable imperfections that slow it down, these are not dramatic forces, yet given time, that top will spin more slowly. A pulsar experiences something similar, though the mechanism is far more subtle and profound. The young pulsar, blazing with the fury of its recent birth, might spin hundreds of times per second, its energy output staggering. But gradually, over the course of 1 million years, or 2 million, or 10 million, that frenetic rotation begins to ease. The spin rate decelerates. The intervals between its pulses grow longer and longer still. The radio beams sweep across the cosmos with diminishing vigor. Where once a pulsar sang with urgency and brightness, it begins to hum more softly, and that hum begins to fade. This is not a catastrophic process. There is no sudden rupture, no violent collapse. It is instead the gentlest of transformations, woven into the very fabric of how these objects exist. And in a certain way, there is something comforting in this fate. Every star, no matter how bright, must eventually yield. Even the most precise timekeeper in the universe bows to entropy, to the laws that govern the flow of energy and the arrow of time itself. A pulsar that once regulated its surroundings with atomic precision gradually becomes less useful as a cosmic clock. Its pulses arrive a fraction more slowly. Its radio signal grows weaker. The astronomers who track it must use increasingly sensitive instruments to detect its presence. Eventually, after millions of years have passed, a pulsar may slow to the point where it no longer emits detectable radio waves at all. It does not vanish. The neutron star remains, still extraordinarily dense, still possessing all the gravity it ever held, but its lighthouse beam no longer sweeps across the galaxy. It becomes what astronomers call a recycled pulsar, or, in some cases, simply a neutron star that has retired from the cosmic stage. In a sense, it fades into the great invisible population of stellar remnants that drift through the darkness, undetected and peaceful. This process raises a gentle question. How many quiet neutron stars are out there, no longer pulsing, no longer announcing their presence? The honest answer is that astronomers do not know. There may be far more silent, invisible neutron stars scattered throughout the Milky Way than there are detectable pulsars. The pulsars we observe are the ones whose rotation axis happens to point in our direction, whose beams sweep across our part of the galaxy. For every pulsar we detect, there might be dozens or hundreds of neutron stars that have faded below the threshold of our instruments, or whose beams simply do not reach Earth. And yet this is not a lonely fate, nor a tragic one. The slowing pulsar is following a path written into the mathematics of the universe itself. As its rotation gradually decelerates, the pulsar moves toward a kind of equilibrium. The energy it has accumulated through its violent birth is released, particle by particle, photon by photon, back into the cosmos. The magnetic field, though still immensely powerful, continues its subtle influence on the charged particles around the neutron star, but with ever-diminishing effect. After countless millions of years, the pulsar becomes indistinguishable from any other neutron star in terms of its radio emission. It is still hot, in a certain sense radiating heat left over from its formation into the cold of space, but its distinctive voice, that regular beacon that made it recognizable to our telescopes, has been silenced. This silence need not be thought of as an ending. Consider instead the perspective of deep time. A pulsar that has slowed over 10 million years, or 100 million years, is still far younger than our solar system, which is itself only about 4.5 billion years old. These objects will continue to exist, cooling and slowing, for timescales that dwarf the lifetime of stars like our Sun. Somewhere in the distant future, billions of years from now, a neutron star born from today's stellar collapse may still be drifting through space, faint and invisible, yet eternally present. There is a kind of peace in contemplating this extended, gentle decline. The pulsar does not rage against the dimming of its light. The laws of physics allow no room for such protest. Instead, the pulsar simply is, gradually releasing the energy of its birth back into the universe from which it came. Its rotation slows, its signal weakens, and eventually, to our instruments, it becomes one with the darkness. Yet in that darkness, it remains, a compact remnant of what once was a giant star, now squeezed into a sphere perhaps only 20 kilometers across, hurtling through the galaxy in solitude. Its gravity still bends the space-time around it. Its magnetic field, though no longer broadcasting its presence across light-years of space, still shapes the particles within its immediate vicinity. The pulsar does not truly die. It transforms. It transitions from an active, communicative object, a beacon, a signal, a presence that demands to be acknowledged, into something quieter, more internal, more at peace. And when you consider the vast timeline of the cosmos, when you recognize that pulsars represent merely one chapter in the billion-year story of stellar evolution, there is something deeply soothing in their eventual fate. Nothing lasts forever in its current form. Nothing must struggle against the gentle pull of entropy and decay. Instead, all things eventually settle into quieter states. The universe, in its wisdom, allows these brilliant cosmic machines to wind down, to rest, to fade into the background hum of creation itself, exactly as all things must in the end. Yet for all their precision, for all the ways we have learned to read their clockwork signals across the dark, pulsars still hold secrets that remain just beyond the reach of our understanding. Even now, after more than 50 years of observation, astronomers find themselves sitting with questions that have no clear answers, mysteries that arrive like gentle puzzles rather than urgent riddles demanding to be solved. One of the most curious of these puzzles is something astronomers call a glitch. Imagine a pulsar spinning with perfect regularity, its rotation so predictable that we could set our clocks by its rhythm, and then suddenly, without warning, it speeds up. The rotation period shifts slightly, almost imperceptibly, yet detectable through careful measurement. And then, just as mysteriously as it arrived, the glitch begins to fade. The pulsar gradually returns to its expected pace, as though nothing had ever interrupted its eternal turning. What causes these interruptions? The honest answer is that we do not entirely know. One possibility that physicists have explored with great care is the idea of a starquake, a sudden adjustment in the crust of the neutron star itself. Picture, if you will, the solid surface of this impossibly dense sphere cracking and settling, the way the Earth might shift and release tension. If the neutron star's crust were to reorganize itself, even by the smallest of increments, it could cause the rotation to speed up momentarily, like a figure skater pulling in their arms to spin faster. But no one has yet observed this directly. We are working with inference, with theory, with the faint traces of evidence scattered across decades of observation. There is another possibility, equally intriguing and equally mysterious. Deep within the neutron star, beneath that rigid crust, there may exist something called a superfluid, a quantum state of matter in which friction ceases to exist entirely. This inner superfluid might spin at a slightly different rate than the outer crust, and every so often, through some mechanism we have yet to fully comprehend, the two layers might exchange angular momentum. The inner superfluid, spinning perhaps faster or slower than the outside, could suddenly couple itself more tightly to the crust, causing that telltale acceleration. It is a beautiful hypothesis, elegant in its way, and yet confirmation remains elusive. We observe the glitches, we catalogue them, we compare their patterns, but the mechanism itself stays hidden within layers of matter so extreme that they cannot be recreated in any laboratory on Earth. And this brings us to another profound mystery. What is happening inside a neutron star? We know its mass, we know its rotation rate, we can measure the strength of its magnetic field with remarkable precision. Yet the internal structure, the arrangement of material beneath that crusty surface, remains largely opaque to us. Is there truly a superfluid layer deep within? What is the precise state of matter at the very core, where densities become so great that all our familiar physics begins to fail? Do exotic forms of matter exist there? Quark matter, perhaps, or something even stranger that we have not yet named? These are not failures of knowledge, so much as invitations to deeper wondering. They are the questions that drive astronomers to build better telescopes, to design more sensitive instruments, to pool their observations across continents and years. Each glitch recorded, each timing anomaly noted, brings us incrementally closer to understanding what lies beneath the neutron star's gravity-flattened surface. Consider, too, the broader architectural mysteries of the pulsar itself. We see the beams of radiation sweeping across space. We measure their timing with atomic precision, yet the exact mechanism by which a rotating magnetic field generates such narrow, focused beams of energy remains not entirely settled. How do the charged particles accelerated near the magnetic poles produce such coherent, directed radiation? What determines the shape and intensity of the beam? Why do some pulsars emit signals primarily in radio frequencies while others blaze across the universe in X-rays or even gamma rays? There is also the question of pulsar wind nebulae, those glowing shells of energy and particles that often surround young pulsars, illuminated by the constant stream of particles flowing outward from the rotating neutron star. We observe these nebulae with our telescopes. We watch them expand and fade over centuries, yet the precise physics of how the pulsar's spin energy converts into this spectacular outflow of particles and fields remains an active area of research and modest debate. It is as though each pulsar is a small engine of transformation, converting rotational energy into complex structures, and we are still learning to read the designs it creates. And then there are the rarest, most peculiar pulsars of all, the magnetars, as mentioned before, with their extraordinary magnetic fields, and also the intermittent pulsars, which seem to switch their radio emission on and off, according to their own inscrutable schedule. Why do some pulsars simply stop emitting for weeks or months, only to flicker back to life as though waking from a dream? What initiates these cycles? Here, too, we stand at the edge of understanding, offering provisional explanations while recognizing that the full picture remains incomplete. What makes these mysteries so beautiful, perhaps, is that they are not terrifying gaps in knowledge. They are gentle, open questions, invitations for future observation and thought. They suggest that even after all our technological progress, even with all our instruments and mathematics, the universe still preserves pockets of wonder, small corners where the familiar rules become uncertain, and where curiosity remains genuinely alive. These mysteries remind us that comprehension is not a destination but a journey, one that unfolds slowly, patiently, across the work of many minds and many years. And that incompleteness, that recognition that much remains unknown, somehow feels restful. It absolves us of the need to have all the answers immediately. It allows us to sit with the questions, to turn them over in our minds the way one might hold a smooth stone, appreciating its weight and texture without needing to understand its deepest interior. The pulsars will continue spinning through the darkness, keeping their secrets, gradually revealing themselves to those patient enough to listen across the vast distances of space and time. When you imagine the Milky Way, that vast spiral of light and dust stretched across the night sky, you might picture it as a single frozen moment, a snapshot of starlight fixed in place. But in truth, pulsars are scattered throughout this island universe like countless ticking clocks, each one broadcasting its steady signal outward into the darkness, each one a message sent across the vast gulfs of space, traveling for years and decades and centuries before reaching our waiting antennas here on Earth. These signals, when they arrive, are impossibly faint. A pulsar's radio emission, by the time it reaches us, carries barely more energy than the heat from a drop of water falling from a great height. We detect them only because our instruments have learned to listen so carefully, to gather photons and electrical pulses with extraordinary patience and precision. Consider for a moment the journey that a single pulse must take. It leaves a pulsar somewhere in the galaxy, perhaps in the Orion Arm where our sun resides, or perhaps in the Perseus Arm billions of kilometers away, and it travels outward at the speed of light through a medium that is far from empty. Interstellar space, though nearly a vacuum by our earthly standards, is threaded with clouds of gas and dust, with free electrons drifting between stars, with magnetic fields that gently bend and scatter the electromagnetic waves passing through them. The lower frequency radio waves travel slightly slower than the higher frequencies, so by the time a pulsar's multi-frequency signal arrives at Earth, the lowest notes have been delayed by fractions of a second compared to the highest ones. This dispersion, as astronomers call it, actually allows us to estimate how far away the pulsar lies, reading the distance in the delay between the notes of its cosmic music. The Milky Way contains something on the order of 100 billion stars, and of those, perhaps 1 million have ended their lives as neutron stars. Not all of those neutron stars become pulsars. Many spin too slowly to be detected, or their beams point away from us entirely, hidden by chance in the geometry of space. But estimates suggest that between 10,000 and 100,000 pulsars may actually exist within our galaxy right now, most of them too faint, or too distant, or too misaligned for us to ever discover. When you consider that number, something begins to shift in your mind. You realize that the universe is not sparsely populated with these objects. Rather, the Milky Way is thick with them, layered through its spiral arms and disk and bulging center, a population of stellar remnants so numerous that they might constitute one of the most common types of remnant in the galaxy, rivaling or perhaps exceeding the count of white dwarfs. What draws us to catalogue them, to spend hours and hours listening for their faint pulses, is not merely the exercise of discovery itself, though that holds its own quiet satisfaction. It is that each pulsar is a messenger, bearing information from the moment of its birth and the eons of its existence. When we detect a pulsar, we are reaching backward in time, touching the light or radio waves that departed when the universe was in a different state, when that star was still alive, before its death sent a shockwave through space and left behind a spinning, magnetized core. Some of the pulsars we observe today were born thousands of years ago. Their signals have been traveling through the dark ever since, crossing the orbits of planets and asteroids, passing through nebulae and around black holes, occasionally bending slightly as they skirt the edges of massive objects whose gravity pulls at the very fabric of space-time. There is something profoundly humbling in contemplating this dispersal, this spreading out of signals across billions of kilometers. Picture, if you will, a network of lighthouses scattered throughout a vast, dark ocean. Except this ocean has no surface, no boundaries, no edge where the water ends and something else begins. Each lighthouse spins at its own rate, flashing at its own frequency, yet all of them are connected by the fundamental laws of physics that govern their behavior. A pulsar in the Cygnus constellation sends out its beam every few seconds. Another, 200 light-years distant, pulses dozens of times per second. A third, perhaps on the other side of the galaxy, ticks with mathematical precision that would make a metronome weep with envy. Yet they are all part of the same system, governed by the same gravity, the same quantum mechanics, the same stellar physics that brought them into being. The distances involved are so enormous that language begins to fail us. When we say a pulsar is 1,000 light-years away, we mean that its light has been traveling through space for 1,000 years to reach us. If you were to send a radio signal to that pulsar and wait for a reply, assuming it could somehow answer, you would need to wait 2,000 years to hear back. By the time your message arrived, civilizations that exist today would have risen and fallen multiple times over. And yet, the signal from that pulsar travels the same distance in the same time, arriving here night after night, year after year, with the consistency of a distant drumbeat, so faint that we must build special instruments to hear it, and so steady that once we have heard it a few times, we can predict with uncanny accuracy when the next pulse will arrive. Perhaps what makes this contemplation so restful, what makes it such a gentle meditation, is the way pulsars transcend our ordinary notions of time and distance. On a day-to-day basis, we exist within a small bubble of perception. We know the distance from our homes to our workplaces in terms of minutes or hours. We experience time in heartbeats and breaths and days and seasons. But the pulsar asks us to expand outward, to imagine light years instead of miles, to think in terms of thousands of years instead of years, to consider an object so dense that all the mass of the sun is squeezed into a space smaller than a city. And in doing so, something within us settles. Our anxieties, our pressing concerns, our sense of urgency, all of these seem to shrink to their proper proportion when we contemplate the vast, slow, steady dance of the cosmos. The ancient astronomers who looked up at the night sky and saw only the stars had no idea that scattered throughout the galaxy were these rapid spinning remnants of stellar death, these lighthouses whose beams would never sweep across Earth because their geometry was wrong, because the odds of alignment were infinitesimal. They could not have known that one day, centuries later, we would build machines sensitive enough to detect those beams, to capture their faint signals, to piece together the story of how a star lived and died and transformed into something utterly alien. Yet in a sense, those pulsars were always there, always broadcasting, always a part of the grand tapestry of the universe, whether or not anyone was listening. And so we arrive at the quietest understanding of all, one that belongs not to the instruments or the astronomers, but to the cosmos itself. Across the vast expanse of our galaxy, those ancient stellar hearts continue their work, unseen and unheard by human ears, yet somehow present in the mathematics that governs everything. The pulsars are still there, still spinning, still sending their beams through the dark, like the ticking of an infinite clock that has never once stopped keeping time. Billions of them, perhaps, scattered throughout the Milky Way and beyond, each one marking the seconds, the milliseconds, the rhythms of a universe that moves with more patience and precision than any mortal mind could truly grasp. And in understanding them, we have come to understand something else entirely, something about ourselves. For we are creatures who measure time, who count moments, who seek in the cosmos reflections of our own desire for order and meaning. We found in those pulsar signals not just a scientific curiosity, but a kind of cosmic reassurance, that in a universe of chaos and expansion and entropy, there exist these perfect metronomes, these dependable lights that sweep across the emptiness in patterns so regular you could set by them the most precise instruments humanity has ever built. What does it mean to contemplate a heartbeat that has continued for millions of years without faltering? What comfort lies in knowing that somewhere in the depths of space, a dead star's core continues its faithful rotation, its magnetic field still guiding its beam, still reaching across the darkness toward us? There is a profound gentleness in this knowledge, a kind of peace that settles over the mind when you realize that regularity and stability exist not just in the small and controlled corners of human experience, but woven into the very fabric of creation itself. The pulsars do not spin for us, and yet their steadiness speaks to something deep within us, some part of the human spirit that finds solace in rhythm and repetition. Perhaps it is because we are rhythmic beings ourselves, our hearts beating, our breath flowing in and out, the tides of our biology governed by cycles and cycles within cycles. And when we listen to the universe's steady pulse through those ancient neutron stars, we are somehow listening to ourselves, the universe breathing, the universe keeping time, the universe, in its own way, alive. There is no urgency in a pulsar's rotation. There is no haste. A millisecond pulsar may spin hundreds of times in the blink of an eye, yet there is nothing frantic about it. It is simply continuation. It is the idea that something can spin that fast, that precisely, for that long, without uncertainty, without doubt. The thought itself becomes a kind of meditation. The repetition becomes a rhythm you can almost feel, almost hear, almost sink your own breath to. Imagine that regularity extending not across minutes or hours, but across eons. Imagine being connected, through the act of observation and understanding, to a phenomenon that has continued its elegant dance since long before human consciousness existed, and that will continue long after we are gone. That is the true gift of the pulsars. They teach us that we are not the measure of all things, and that is not frightening, it is liberating. In that vastness, in that scale, there is a freedom from the small anxieties that crowd the waking mind. The pulsars will keep their rhythm whether we worry or rest. They will continue their eternal turning, indifferent to our struggles, and in that indifference lies a strange kind of peace. The universe does not rush, the universe does not pause. It simply moves with a steadiness that has no beginning and in some sense no end. Not an end of stopping, but an end of transformation into something we cannot yet imagine, and perhaps that is the most soothing thought of all. To consider that all the energy, all the motion, all the vast machinery of the cosmos is ultimately governed by laws so elegant, so harmonious, that we can predict it, measure it, understand it. The pulsars are proof of that. They are the universe keeping faith with itself, maintaining order in the midst of infinite space and infinite time. They are the heartbeat that never tires. They are the light that never truly goes out. And as you drift deeper now, as your own breath slows and your body releases its hold on wakefulness, you might imagine yourself in tune with that rhythm, not resisting it, but moving with it, letting the infinite steady pulse of those distant stars, those massive collapsed cores still radiating their beams into the darkness, settle over you like the gentlest of blankets. The universe is keeping time. It has been keeping time since long before you were born. It will keep time long after you sleep. And in that knowledge, in that assurance of an order deeper and older than any individual life, there is a rest that runs very deep. The pulsars ask nothing of you but to acknowledge them, to know they are there, to let their steadiness become, for just a moment, your steadiness too. A shared rhythm, a shared breath, the eternal turning of the cosmos, and you, for just this moment, turning with it, into the quiet, into the dark, into the gentle, never-ending pulse of light and time that spans the very heavens.